Hello, everyone. Today, I'll be talking about our paper, Compass Encrypted Semantic Search with High Accuracy. And this is a joint work with Liana at Stanford and also Matei and Raluca at UC Berkeley. So let me first give you a quick refresher on how semantic search works. So usually, semantic search starts with a vector database that encodes one or more categories of data. So when a query comes in, it will be first converted into the vector within the same embedding space. And the search results depends on the similarity between the query embedding and each entries in the vector database, according to some distance metric. So semantic search becomes really popular due to its high quality results and multimodal capabilities. For example, Google used semantic search, and the result will appear on the top page. You can even ask Google, does Google use semantic search? And of course, you'll get an affirmative answer. So whether you're using an Apple or Android device, now you can quickly search for photos in your personal photo library just by describing them in text or voice. Moreover, workspace applications such as Notion and Slack also benefit from semantic search to help users to fetch the information more efficiently. So in these examples, while Google primarily search over public information, the other applications involve searching private or sensitive proprietary data. And unfortunately, data breaches still happen. Let's take major incidents like Capital One in 2019, MongoDB in 2023, and more recently, Snowflake in 2024. During these breaches, millions of users' private records were compromised. And now, in the age of AI, there's growing concern about protecting personal information. All these examples highlight how important it is to protect our private data on the cloud. So clearly, to protect personal data while still enjoying the benefit of semantic search, we really need a scheme that allows us to search over encrypted data. And that's exactly where our system, Compass, comes in. So Compass focuses on semantic search over an outsourced and encrypted database of embeddings. On the client side, the retriever takes the user query, interacts with the server using Compass protocol, and returns a ranked list of document IDs. Here, we're only caring about the document IDs since secure retrieval of the actual document can be done through another layer of Oblivious file system, which is not the focus in Compass. Compass tries to achieve 3 goals. First, we want our system to achieve the search quality that is on par with the state-of-the-art plaintext search. Second, we want efficiency. More concretely, we want both computation and communication overhead to be sublinear to the size of the database. Finally, we want security. But for security, let's first take a look at our threat model. So in Compass, we assume the client owns the data stored on the server, and therefore it is trusted. The server, on the other hand, can be malicious, which means it can deviate arbitrarily from Compass protocol and try to steal users' data. More importantly, we have no trust assumption on the server side. This means that we don't rely on any trusted hardware, as it can be vulnerable to many side channel attacks. We also don't rely on non-colluding assumptions, meaning that you can deploy our system securely with just a single logical server. For concrete security goals, we want to make sure that server cannot learn anything from the database, from the query, and the results, which means we also need to hide access patterns. And the server cannot tamper with the search results without detected by the user. And the security non-goals here, including timing channels and DDoS attack, which is common practice in the literature. Now, let's take a look at some prior works to see if they can achieve the same goal in our setting. So there's actually a very long line of work in the encrypted search literature. Traditionally, a lot of schemes are built based on lexical search or keyword matching, and therefore, they suffer from limited accuracy. To gain efficiency, these schemes usually compromise on security, such as leaking part of the search result, rely on trusted hardware, or having multiple non-colluding servers. More recently, there have been a few work on encrypted semantic search. However, their search quality remains limited due to their underlying index construction. These schemes only achieve sublinear complexity in communication and don't provide any protection against malicious servers. Now, let me show you how to achieve all these 3 goals with our system Compass. To design Compass, the first question we want to answer is how to achieve the state-of-the-art plaintext search quality. Of course, not through a linear scan. So we start by looking to a state-of-the-art plaintext search index called Hierarchical Navigable Small World. And HNSW is proposed in 2016 and has been already adopted into vector database company like Qgen and Pinecone. As you can see, HNSW consists of multiple layers of proximity graphs, and each higher layer is a subset of the layer below. The top layer of HNSW has the fewest nodes with longest edges, for rapid traversal, and the bottom layer contains all the nodes in the database with shortest edges for precise search. Search in HNSW starts with a predefined entry point at the top layer. From there, it performs a greedy search to find local minimum. Once the local minimum is found, the search moves down to the next layer and repeats the greedy search process. These steps continue layer by layer until the nearest node is found at the bottom layer. But now the question is, how do we support such a complex graph work in a secure way? So Compass adopts an idea of compute storage separation. Namely, we treat the server purely as remote storage while executing the search algorithm locally on the client. So whenever the client needs some data, such as embeddings or enablers, it retrieves them directly from the server in the encrypted form and decrypt it. To ensure the server learns nothing from the request, we must also ensure that the access of the data is oblivious. So one might consider using a cryptographic primitive called private information retrieval. Well, unfortunately, PIR increases a cost that scales linearly with the size of the database, making it impractical in our case. So instead, we consider another approach called Oblivious RAM, which is proposed by Goldbridge and Ostrovsky back in 1996. ORAM is a cryptographic technique that hides access pattern to storage, ensuring that an observer cannot infer which data is being accessed. So here's an example. On the left side, let's say the user is interested in the second entry of the database. And on the left side, without ORAM, the user directly fetches it from the server. And the server clearly sees which entry is being accessed. However, on the right side, with ORAM, the user's request will be first translated into a series of requests that appear random to the server. And therefore, server learns nothing. So right now, a quick summary of the ideas we have. We have HNSW to ensure logarithmic search complexity. We have Oblivious RAM to ensure the security and the benefits listed here. Are we done? Not yet. So the challenge is really HNSW is designed for local search, and directly applying HNSW over ORAM is going to be super inefficient. And let me show you why with this toy example. So here we have a graph. You can consider it as one layer from the multi-layer structure in HNSW. And here's the entry point. If we start our search, we can check the neighbors of the current node and select the one closest to the query. And we then move to that node and repeat this process until none of those neighbors bring us closer to the query. So in this case, we find the nearest nodes. And the numbers here represent which search step this node is being selected as candidate. So let's take a look at the cost of this process. So in this search process, it takes 7 search steps and 13 visit nodes to reach the nearest nodes. Why do I care about these two numbers? Well, the number of search steps is actually the number of round trips you're going to need for the search request, and the number of visit nodes represents the amount of network bandwidth you need during the search. In a real example like CIF 1 million, it takes 36 search steps and more than 1,000 visit nodes to achieve good accuracy, which means that such a high network round trips and high network bandwidth requirement makes the system really impractical. So in Compass, we perform a co-design between the search algorithm and crypto primitive. Specifically, we have over the network Graph-Traversal algorithm, which I'm going to talk about today, and Graph-Traversal Tailored ORAM, which I'm going to just briefly cover due to time constraint. So in our Graph-Traversal algorithm, we have 2 concrete techniques. The first one is called Directional Neighbor Filtering, which reduces network bandwidth, and the second is Speculative Neighbor Prefetch, which reduces network round trips. The key idea of our Directional Neighbor Filtering is to consider only a subset of neighbors that are in the direction to the query. Like the kit here, it would be great to have a compass in hand to show you what's the right direction. And that's also part of the reason we name our system as Compass. So back to the graph example, if we start from the entry point, we consider this as the direction from the entry point to the query. And out of its 6 neighbors, we consider these 2 nodes are in the direction to the query. But now the question is, how do we determine the direction of the neighbors without even knowing their coordinates? So our idea is to have a quantized database stored locally on the client and serve as the hint. So specifically, we're using product quantization. The benefit of product quantization is it has very high compression rate. So empirically, the client-side index, the client-side hint is only 1 to 3% of the original database size. And if you're familiar with the quantization, you may wonder, isn't quantization lossy? Well, that's true. If you build a search index directly over quantized vectors, you'll get a huge accuracy drop. But here, what we found is that this quantization method is accurate just enough for serve as the directional filter. Okay, so let's say if we pick 2 neighbors per candidate, And here's how search proceeds. Yes, we find the nearest neighbor. And with this technique, let's take a look at the cost. So we still require 7 search steps, but we reduce the number of visit nodes from 13 to 7. And empirically, this saving over network bandwidth is going to be about like 10x. Our next technique is called Speculative Neighbor Prefetch. The key idea is to speculatively retrieve likely needed nodes alongside the currently needed nodes. So like in this graph, we're sending multiple kids at the same time to explore different paths simultaneously, hopefully increase our chance to reaching the destination faster. Back to the graph example, according to the search algorithm, we know that this node is currently needed. But if you still remember the whole search process, we know that this node is going to be likely needed. And if we can explore these 2 nodes at the same time, that would be great. But the question is, how do we guess the likely needed node? Well, fortunately, in greedy search, we have this local candidate set, and we can simply select more than 1 candidate at the same time. So back to the example, if we select 2 candidates nodes per step, and here's how search proceeds. So in this case, the cost with this technique, we reduce the number of search steps from 7 to 4, while the number of visit nodes is still the same. So empirically, according to our experiments, the savings on network round trips is between 2 to 16x, depends on the actual workload. So one nice thing about these 2 techniques is you can just combine them together and get the best of both worlds. So on the left side is the classical greedy search where you need 7 search steps and 13 visit nodes. And the right side is the compass search algorithm where you only need 4 steps and 7 nodes. And these empirical saving numbers are I just mentioned. And for the ORAM, for the Graph-Traversal Tailored ORAM, we make a white box adoption of ring ORAM based on 2 observations. First, the requests to neighboring nodes within the same search step can be batched. So this gives us less network round trips. And second, nodes are visited at most once during a search request, which means that eviction, which is the operation used in ORAM, can be deferred until the end of the query. This gives us better user perceived latency. So of course, for more details about this technique and how we ensure integrity against malicious server, please check our paper. And since we made a white box modification on ORAM, we also have to revisit the stashed usage and security proofs. And we provide a formal analysis of both of them in the paper as well. OK, so now let's take a look at the evaluation. Our setup consists of 2 cloud instances simulating the user device and the server. We have 2 sets of bandwidth and round-trip latency configuration between these 2 instances to simulate the same region and cross-region networks. We evaluate our system across 4 classical semantic datasets. 2 of these datasets are text-based, and the other 2 are image-based. The size of these datasets range from 100,000 to 9 million entries with different embedding dimensions. And this will help us to evaluate our system at different scale. So in terms of baseline, we have 2 secure baselines here. The first one is called inf-ORAM, which is for text-based datasets only. So basically, this baseline is built with an inverted index stored inside of ORAM. And the relevance score is computed using the classical lexical search algorithm TF-IDF. The second baseline here is called HE cluster, where we basically use homomorphic encryption to compute the similarity score between the query and each entries in the database. And then we use the idea of clustering to reduce the communication to sublinear. So for search quality, we use the metric mean reciprocal rank at 10, where reciprocal rank is the inverse of the rank of the first relevant item in the results. Basically, the higher is better. So if you compare our system against these 2 baselines, you can see that Compass outperforms both baselines, especially on larger and more complicated datasets like triplet and MS-Marco. And if you compare to our system against vanilla HNSW, you can see that we indeed matches the accuracy of the plaintext vanilla HNSW. Even if you compare it to, so we have an extra column called optimal here. This is generated through running a linear scan over the whole data set, which kind of gives you the sense of the highest search quality you can get under the current embedding model. So our search quality is still not too far away from that. Finally, here's a comparison of the end-to-end latency between Compass and 2 baselines over cross-region networks. As you can see, Compass achieves a search latency ranging from 0.6 to 1.3 seconds, which is orders of magnitude faster than the 2 baselines. And these 2 numbers are kind of practical, even in a real use case. And more importantly, if you look closely at these 2 datasets, triplet and MS-Marco, even though MS-Marco is like 6 times larger than triplet, in Compass, we only need like 0.16 seconds, which shows the efficiency of our system. So in conclusion, Compass is a semantic search system over encrypted embedding that matches the accuracy of state-of-the-art plaintext search algorithm, achieves practical user-perceived latency, and provides very strong security against malicious servers. And here are the QR code to our paper and code. Thank you for the time. I'm happy to take any questions.